Um, Anyway, let's start this class at least, and then we'll see how it goes. So we were discussing about something called virtual memory, and so I hope this is clear. If you have questions, we are very few people, so you can just bring that question up, and I'll be able to answer. So we said that we will divide the actual physical memory into four chunks or four pages or four segments, whatever you want to call it. It's generic for page. So I'm calling it as capital A, B, C, D. So it's a 256 byte memory. So I have divided it into 64 byte each. Similarly, when a process comes, I create a virtual address space. Sorry, a virtual address space of 256 bytes, 0x0 to 0xFF, and it's 64 byte each. So I have created a virtual address space of 256 bytes, and then I have just divided it into 64 byte chunks each again. Similarly, whichever process comes, I create a virtual address space of 256 bytes and have a division among the 256 bytes as 64 bytes each. This is all virtual division. It's not in reality. And then I also maintain a page table per process. So I say, okay, I have a page table, a page translation table, where each of the page gets mapped to the physical page. So here, the small a is mapped to capital A, which means that the small virtual address A is mapped to a physical page A. And then this B is mapped to D here, and C is mapped to capital B. And D is not yet mapped, which means that this is in the hard disk, so the secondary storage. So in the secondary storage, I am assuming that whatever virtual address space that I am creating is already available here. Not just this, but whatever the process has requested for. And by swap in and swap out, let's say, and this small a has been allocated in capital. So now, if the process 0 generates an address 0x83, I directly, of course, cannot access the cannot directly access the physical memory. So I go to the table, I see, okay, the 0x83 is C, so it's mapped to capital B, so the reality is 0x43, and it will access this particular 0x43. So I always access the table and then try and get the physical address and then go to the main memory, access that. If it might be so that there is a miss, let's say P0 generated, P0 generated, in this case, P0 generated 0xC3. So you know that if I know that 0xC3 is not yet mapped, which means that it is here. So it's a page fault or a page miss. So I bring that particular D to somewhere here and then access that memory. So I hope this working is clear. If it's clear, we will move to the next part of it. Now, are there any questions regarding this? If you had a chance to give it a thought. So any question is fine. Okay, so let's assume that you have no questions and go forward. So we said, okay, I mean, we also said that you can have virtual address space of any account quantity you have. It does not depend on the actual memory that you have, as long as you are okay with the speeds that you get. So you can have like 1 terabyte of memory supported. And assuming that you are not worried about the page table size and things like that, it still works. I mean, this idea still works. Now, one of the important questions that we wanted to answer in the last class is, we know that every process now has a page table. This process has a page table. And what is the page table telling me? The page table is telling me whether what particular page this page has been mapped. So now, where do you want to keep this page table? So any thoughts on where do you want to keep this page table? I can keep it here, I can keep it here, or I can keep it as a separate hardware. So where do you want to keep it?
In processor.
Huh?
Can we keep it in processor?
Yeah, in processor means where? I mean, can you tell me where the hardware is? Is it here? Is it next to the register?
Yes, sir, I think.
Okay. So now the question that we were answering is, where is this table stored, right? Virtual page table stored. So now one of the answers that we are saying is we want to keep it in the hardware here. Okay. So now I have this particular 256 bytes of memory, and I have divided it into chunks of 64 byte each, and each process has a table. So let's assume there are 4 tables, right? Let's assume that the number of entries in this table in this particular, let's say the process is 0 is also given 256 bytes, process 1 is also given 256 bytes, so on and so forth. Okay. So how many entries are there in the table of process 0? How many entries are there? Any guess?
4.
4, right? Yes. 4, and each entry will be of some size, right? Let's assume that it is around 2 bytes or 3 bytes or 4 bytes or whatever it is. You can actually calculate that because you know the address size, right? Okay. So now, let's say I have allocated 4 entries here. So this is hardware. You should remember that this is hardware. So I have a hardware structure which stores 4 entries. Now, do I create one more hardware structure here? So this is for process 0. Should I create one more process or one more hardware structure here? So this also has.
So I think this needs to have like a software component because process 0, any process can have any number of entries, right?
No, not really, because
So how can you?
I can have an upper limit on it. So if I have a process 0, I am saying the address space is 256 bytes alone. I am not allowing it more than 256 bytes. Okay.
Okay.
So which means that how many entries are there in the page table of this process 0? So this is the this is the virtual address. This is the physical address page. I am not only talking about physical virtual address. So maybe this A, B, C, D, 4 entries are there. Maybe this is mapped to A. This is not mapped. This is mapped. Maybe this is mapped to C, right? But there are only 4 entries, maximum 4 entries. If the process has not, so I have told the process that you are given 256 bytes, but maybe the process might not be using 256 bytes. Maybe it is using only 128 bytes. Then it might only have 2 entries. But I can have an upper limit on the number of entries in the process table, right?
Okay, sir. Yeah.
So I have 4 entries here. Okay, so this has 4 entries. I mean, this is all. I mean, whatever I'm telling you is actually wrong, but I'm just telling you so that you understand where is the complexity coming from. Let's put for process 1. Okay. There are another 4 entries. Okay. Now let's say process 2 comes. Now where will you keep this process 2 stable entry? So
by going this method, may I have to build one another for P2 also.
Yeah, so can you build a dynamic hardware? Can, like, depending on the number of processes that you get launched, can hardware be dynamically built?
No, sir.
No, right? So I mean, you have already manufactured the chip, so I can't have these processes here, right? So I can't have a process table like this in the hardware, because you have to remember that the hardware, you have to fix it before it, and you don't know how many processes that you will launch, right? And as Debussy pointed, there is of course this issue that if I give more than 256 bytes to the process, then the number of entries in the table keeps going up. So generally, if you say in today's world, you can have memories up to say kilobytes to 60 kilobytes. The number of entries in the process table are pretty huge. So I cannot have a table per process as a hardware structure. So I hope everybody is convinced. You are convinced. I am assuming that you are convinced about the fact that you cannot have a hardware page table per process. Okay.
Sir, can we make something before introducing that virtual memory address, you built a table, right, which was checking for the security issue one.
Yes.
In the side, you built another table, and then that method can we take?
Yeah, in the table, what will you keep? But no. I mean, let's come to the table. I mean, let's worry about it later. But I'm asking now. Now, see, is everybody convinced that I want to have look, first thing, there are 2 things that you have to be convinced about. One is, are you convinced that every process needs a page table entry or a page table?
Yes, sir.
Yes, right. So every process that I launch should have a page table. Okay. And
sir, these processes are not running parallelly, right? We are switching between the processes.
Yes, right. Yes,
okay,
you are
sir.
right. Yeah.
Okay.
Yeah. I mean, we are as of now assuming only one CPU, one thread CPU. Of course, you can imagine that it gets even more complicated or complex if I have multiple threads and multiple cores and things like that. Okay. So now I hope you are convinced that you need a process table, and you don't have any upper limit on the number of processes you want to launch, because in general today's world you launch hundreds of processes, not just 1 or 2 processes. The operating system itself launches multiple processes, right? So there's one network process that is always listening to the network port. There's one more process which is just doing file system access and things like that. So you have multiple processes that are launched, and you are convinced that you need a process table per process, and you are also convinced that you cannot keep it in the hardware because you cannot dynamically generate hardware. So now what's the solution? Where will you keep this process table?
Sir, if we can upper bound the number of processes,
Mhm.
then we can build the
Okay.
static hardware, right?
Yeah, so let's say I tell you that I'm manufactured a processor which is extremely fast, but you can at any time launch only 8 processes. Will you be okay with it?
I didn't get it, sir.
No. If I put an upper bound, will you buy a processor like that? Like, do you think that Intel can sell a processor which says there are only 8 processes that you can launch at any given point of time? Will you buy that processor?
Maybe not.
Maybe not, right? So, I mean, that's not possible. I mean, it's very difficult to sell such a processor. And it's not just about the upper limit of the processes. So, let's say I have a 64 GB memory support, 64 gigabytes of memory support. And of course, I can have the page size itself as 64 gigabyte. But then I am limited. I need to have the 64 gigabytes of RAM plugged into the system. So generally, you might have an address space. Generally, it looks like this, right? So I have an address space which is around 64 gigabytes, or maybe even higher. Of course, it's even higher. And you actual main memory or the RAM that you plug in, the cards that you plug in is maybe 8 GB. So, but you are supporting 64 gigabytes of address space. And how much page size would you want to have? What is the, so here we had 64 bytes as a page size. I can have 64 bytes as a page size. I can also have 64 gigabytes as a page size, but this will not work here. I can have 8 gigabytes as page size.
Sir,
Like,
one doubt. This address space should not exceed the storage, right?
No, we already saw that
Okay.
it can. We already saw that it can exceed here.
No, the storage, secondary storage.
Yeah, the address space cannot exceed the secondary storage, but 64 gigabytes is nothing by 1 terabyte hard disk. So you're talking
Okay,
about
sir.
this, right? You're talking about this, right?
Okay, sir. Yeah.
Yeah. Generally, there are other mechanisms to handle it. You actually can exceed that, but as I said, that is out of the scope of this particular course, at least because of the time limit. But just keep in mind that let's say I promise 64 gigabytes address space. Okay, you can run it with an 8 GB RAM with only 16 GB hard disk. You can still run it. There are tricks to do it, but as I said, whoever teaches operating system will be teaching you those tricks. But the idea is okay, right? Okay. So now I can have an 8 GB page size, but 8 GB space size. If I have 8 GB page size, what happens? If I have 8 gigabytes page size, what happens?
You use your whole RAM for just one.
For just right. And if I access another page, then I have to swap in and swap out. So generally, people have found out that maybe 32 kilobytes or 8 kilobytes is a very good page size. So now you can think about it, right? So it's like 2 power 6. Now, so the number of entries in the page table. So the number of entries in the page table is how much? So the number of entries in the page table is 2 power 6 into 2 power 20 divided by 2 power 3 into 2 power 10. Is this okay? See, I have 64 gigabytes of address space. I have a page size of 8 kilobyte. Here I had a 256 byte address space. Each page size was 64 bytes. So I got 4 entries. Now the address space is 64 gigabyte. The page size is 8 kilobyte. So the number of entries is 2 power 26 divided by 2 power 13. So it is 2 power 13. Right? So there are around 1024. There are around 8192 entries, right? Is everybody following this?
Yes.
Right. So I can write it as 2 power 3 into 2 power 10. So 2 power 3 is 8 into 1024. I have 8,192 entries in my page table. So now if I launch hundreds of processes, I should have each table 8192 tables, entry tables here. Are you following? I mean, if you're not following, please let me know. Anyway, like you have come like to learn, right? So it's okay to ask questions.
Sir, I was not able to follow.
Okay. So, okay. So did you understand why it is 4 entries here?
Yes, sir.
Okay. So now there is a process. I can have 4, let's say my address space is 256 bytes. Okay. Now I can have a page size. When I say page size, it is the chunk size, this particular size.
Yes, sir.
Okay. So the page size I can have 256 bytes. So the number of, if this is true, the number of entries in the page table that I keep here, right? So this is the page table that I keep, given a virtual page address to physical page address. How many entries will be there?
One only.
Only one. So now if I had, no, but I have seen that I keep 256 bytes and page size as 64 bytes. So the number of entries is 4. That's why you are getting 4 entries. If you remember here, we were getting 4 entries here. Agree?
Yes, sir. Yeah.
Okay. But now I'm just giving you a hypothetical case where, let's say, I want to support 64 gigabytes of address space. This is the address space that I am planning to support. A process can generate any address between 0 to whatever the 64 gigabytes is. Now, what will be the page size? I mean, what do you want to keep the page size as? You can keep the page size as 64, like you can keep the page size as, say, 8 GB. Let's say the main memory was 8 GB. I can keep the page size of 8 GB. Then the number of entries is how much?
8.
8. But what happens if I keep the page size as 8 gigabytes? Then you are keeping only one page at any given point of time in the physical memory, right? So your system will look something like this. You have an 8 GB memory. Let's say you brought an 8 GB memory card and plugged into this. And the process 0 is saying, I have a 64 GB address space, which means that you have divided it into 8 chunks. Right? So maybe you are reminded it as A, B, C, D, and whatever it is. And this you are only one page is there, so you have kept it as capital A. So now at any given point of time, only one page can be mapped to this physical address. Agreed?
Yes, sir.
Right. So what is the disadvantage of this?
Many
Like
page faults.
Yeah, many page faults. Excellent. Yeah. So because if I access something here, then it's okay. But if I access something here, then I have to write this entire 8 GB to the secondary storage and bring that new page here. So it means that there are many page faults. So now people have found out empirically that if the page size is 8 kilobytes or 16 kilobytes or 32 kilobytes, that is more than enough. Of course, we will have one beyond that, but let's assume that it's around kilobytes. So if the page size is 8 kilobytes, how many entries are there? Is the question that I'm asking. So how many entries are there? It is the address space. It has nothing to do with this. So it's the address space. So it is 64 gigabytes divided by 8 kilobytes. Okay.
Yes, sir.
Yeah. So what is 64 giga? Giga is 2 power 20.
Giga means 2 power 30, right?
Oh, sorry. Okay. Yeah, you're right.
That is where I was confused.
Yeah. Okay. Yeah, you can this way. Okay. Yeah, then it's even worse, right? So it's 2 power 36, and then it is 2 power 20, and then it is 0. So you have these many number of entries. So each page table will have these many number of entries, upper limit, and now you want to support multiple processes. So which means that the whole point that I'm trying to derive is it's very difficult to put it in the hardware. Like I cannot have a hardware here, and here because I don't have an upper bound. I don't have an upper bound here. I mean, I cannot put an upper bound here. And the number of entries per table is also pretty huge. So I cannot design a hardware here. Like even if one page table, like let's say it's 1 byte, right? Then 8192 entries will take up 8 MB of data, right? It's not even the cache size. The cache size is only 32 kilobytes. So just to keep the translation, if I'm using 8 MB, then it's not a good solution. So where do you want to keep this page table? Okay, I hope everybody is convinced that it's not straightforward to keep this in the hardware. Does everybody agree?
Yes, sir.
So now where do I want to keep this? So we are back to the same question. So now I can't keep it in the hardware. I'm just convinced myself that I can't keep it in the hardware. So where do you want to keep this page table?
So the only option is software.
Yeah, but what? Okay, it's excellent. You should keep it in the software. But when I say software, where? I mean, do you write it in your code or do you write it in somewhere? And where does that software get mapped to? See, okay. So when I have a system, see, I want the reason I'm stressing this is I want you to understand actually how. I mean, where exactly it is. It's easy to say that it has to be in hardware or it has to be in software. But you have to think about it in terms of, if I have it in hardware, where in hardware? If I have it in software, where does the software get mapped to? So let's say I have a system like this, which a memory of 256 bytes, and I write a process 0 with a code, right? So let's say I write some pieces of code here. I have already convinced myself that this piece of code itself is stored in some memory, right? And that memory is part of this process. Now, I want to keep the page table. Yes, we have convinced ourselves that the page table should be part of the software. But where? I mean, where is that code? And where is that code mapped to?
Sir, maybe it is managed by operating system.
Okay, let's assume that I mean, of course, I haven't even told you that there's an operating system, but let's assume that you know about operating system. Even if you know about operating system, will you just allow the operating system to create a data structure called page table? Let's say I have a process called operating system. Okay, and what you are saying is a process called operating system has a data structure. Right? That's what you are saying. Data structure. Maybe you have a map. Somebody has written it as an STD map, which is just having a key value pair. The key is what? The key is the what is the key? What do you have?
Virtual address.
Yeah, virtual page address to physical page address. So somebody has written this. But where do you want to keep this map? Is it part of, I mean, I can just declare this and forget about it?
So it should be in the main memory sort of thing, right? Not in the second memory. Like you should
Yeah, but
allot a
how?
part of it and always keep it there and not swap it out.
Yes, why?
Otherwise, if you go to the secondary storage every time, it will be.
Yes, right. Let's say I can run only one process. Let's say this is process 0 that I am running, and the other process, instead of calling it P1, I will call it as process operating system. And this process operating system is actually having the page tables of all the processes. Now, when process 0 is running, right, when process 0 is running, this page table itself might not be part of the main memory. Maybe it is in the secondary storage. Then, just to translate the address, you will have to go to the secondary storage, get this particular map it onto the main memory, ask the operating system, hey, this is the virtual address that I have generated, can you convert it? And then run the process 0 for every address. Remember that you are doing it for every address that is being generated. There is no, I mean, I can't do away with it. For every address that is generated, I have agreed that it's a virtual address because it's generated in the dream, and I have to convert this to physical address. So which means that for every virtual address I am generating, I am asking the operating system what is the translation that I have to do, and the operating system is looking into its piece of code and saying, okay, there's a map that is declared here, and that map itself is maybe a vector of maps. Why is it a vector of maps? Maybe because it has multiple processes that it has to support. And now I go to this process 0 vector element, go to the map, get the physical address, and then give it to processor. So then I have made such a complex design that the performance just shoots right. Is everybody following? If you have questions, please ask me. Is this okay?
Yes.
Okay. So now so now what Devesh is saying is, like, there are 256 bytes. Right? Maybe I will earmark this to keep the page table entries. And I will name it as ABC. So I will allow only 3 pages. This page, I will call it as reserved. This is reserved. Who has reserved it? The operating system has reserved it. So the page table entries, some of the page table entries are always stored here in this particular location. Is it okay? Now, when process 0 comes, let's say process 0 comes, it generates a 256 byte. I am allowing it to generate 256 bytes of entries, which means that it can have a map from A, B, C, D. It has a process table, which is part of this reserved space. Maybe, of course, it can be in secondary storage, but let's assume that it's part of the secondary storage. And now you have virtual page address to physical page address. And I have mapped A, B, C, D. Maybe A has been mapped to capital A, B has been mapped to capital C, C has been mapped to capital B, and D has not been mapped. Now, if the process 0 tries to access small letter d, then it has to go to the secondary storage, right? It has to go to, let's say it accesses this, then it has to go to the secondary storage, get that particular d, swap in and swap it. Do you think the system works? Please ask questions. You have woken up very early, right? So you have taken the pain to come. So if you are not understanding, please ask me. Does this make sense to you? So can I just cut off this reserve space like this? This should still work, right? I don't have to have 4 pages here. I don't have to have 4 pages to support 4 pages here. I can support n number of pages here and I only have 3 pages here. This is still perfectly valid. Is this okay?
Sir,
Yes, sir,
but
can we
miss
also-
rate will increase.
Yeah, why miss rate will increase? Because 1 page is lesser. But if I didn't have this reserved space, then every time I might have to go to the main memory, right? That you are convinced.
Yes, sir.
So, I mean, that's better, right? Okay, go ahead. You had some other question.
So we can also like break it off if we don't want the if we don't want to start off the addresses from 0.
Mm-hmm.
Like if you want A to start from the 0th address or something like that, then this part you can kind of have like a complete break from the main memory.
No,
And have separate.
that's hardware. So the hardware circuitry understands that it's from 0x0 to something like. Now, how will I split it? How will I split the decoder? How will I split the multiplexer? See, the hardware
Okay,
RAM. Yeah. So, yeah, I mean, this is, I'm not saying you, but I'm generally saying we are so tuned to using it in the software terms that we finally forget that it's just a circuit. If I have come up with what she's saying is, I will have this as 0x0 and also this is perfectly valid. I mean, you can do it. But the first question I would ask is, forget about the hardware. Is there a necessity to do it? Actually, no.
Yeah, it's not required.
It's not at all required, right? Because it's just in the dream that is being converted to reality. And I'm not worried where my reality is. Even if it is required, it's very difficult to do that. Any other questions? Yeah, please feel free to ask any questions you have. This is, I know that is really new to you, generally, unless you have worked on Linux kernels.
Sir,
Mhm.
Sir, this reserved space may decrease or increase, right, depending on the number of processes.
Yeah, so then you will just have to swap in and swap out. So there are some entries in the reserved space. Of course, this entire map cannot be pushed in the reserved space. Then you will have to swap in and swap out. This also happens to be swap in and swap out. See, even though I call it reserved space, it's the reality of some process. What is that process called? OS. It's just the dream of operating system converted to reality. It is just that you are pinning that. It's like saying the operating system is a bit higher. So I am giving a space, which means when I say reserved, what does it mean? It means that some other process cannot overwrite here. I could have done the same thing for process 0. Maybe, okay. So let's assume that for some hypothetical case, process 0's small letter a is very, very critical. Let's assume that it's very, very critical. Then I can, what could I have done? I could have said that this particular small a, right? This particular small a is always reserved here. This is process zeros, small a. Now, instead of this being A, right? Instead of this being A, now I have this as A and this as B. This would still work. Now, process zeros A will never create a page fault. And I can call this also as result space. Agree? I can do that. I mean, if this particular A, if that is this particular small a is very critical, I can pin this particular A here always, such that whenever process zero generates an address here, it will not result in a page fault. And the remaining 2 pages, I allow somebody else to use, or even the process zero's pages to use. So it is just, when I call it result, there is nothing special about it. It is just that the dream of operating system, some of its dream has been converted to reality, and that reality has already occupied the space. It has like constructed a permanent house here. Others are just moving in and moving out of the city. Is this clear?
Yes, sir. Okay.
Okay. So is everybody happy with this design? What is the issue? There's a big issue with this design.
So can we exceed our? Can we exceed like the limit of this page?
I didn't get you. Limit means?
So like you said that the first block will be the table, right? But first page. But what if the memory limit exceeds that? Like of the processes, like there are so many processes that the table
Yeah.
does not fit into our.
Yeah, definitely. The table does not fit in. That's what. So the table does not fit in here. So it will always be, see, this, that's what I'm saying. So if this, what is this table? This table is just, okay. Let's draw this process operating system. Let's assume the process operating system is also given 256 bytes. Okay. Again, I am repeating it because this is also on video. Some of the things I'm telling you are actually wrong. So you should not take it as the truth. I'm just trying to convince you so that you will finally get the big picture. But some of the things that I'm telling you are I'm fully wrong. I mean, there is not even an iota of truth in it, but this is how the design has evolved. So let's say the operating system process has 256 bytes allocated to it. Okay. So now I again divide it. So let's say I don't consider it as a real different process. Whatever I was dividing it here, I also divide it here. And I also call this as small a, small b, small c, small d. In this address space, this particular map, right, it's again a data structure. So which means that it has to occupy some memory location. Let's say it occupied this particular address location. Let's say it occupied these many things. So it occupied some half page A, half page C, and full page B. Is it okay? It's just a data structure, right? It's like like any other process. Agree?
Yes.
Okay. So now maybe when I say reserved, I am putting only B here. If a process generates an address such that the page map is not available and maybe it falls here. Let's say it falls in this particular, the map is this particular, then what do you have to do? Where is this small a?
In main memory.
Yes, right.
Like
No,
hard
disk, secondary storage.
Hard disk.
Right. Why?
So we
because,
go and
yes, right. You go and fetch. Maybe you keep that small a here in the reserved space. It's just that the reserved space is reserved for operating system. It's not pinning one page. It's like recursive dream, right? It's like recursively page faulting. Of course, now you can ask, like the other question that you can ask is, when the process operating system generates an address, who converts this address? Right? It's like there is a God. Now the God is converting everybody's address, but if the process operating system itself is generating a virtual address, right? So somebody has to convert this virtual address to physical address. Now who is converting this virtual address to physical address? Of course, I can assume that there's super God and there's POS, OS, and that is converting. But now there's no end to this question because you can ask who is converting that virtual address to physical address. Okay. So did you agree? I mean, do you now understand what I'm saying?
Yes, sir.
Okay. So do you think there is no issue with this design? Yeah, anything that you can think of is fine. Forget about this question. That's what happens when process zero generates. This will come maybe as the closing remark to this course, but just don't get confused. Let's assume that the process of operating system is allowed to generate music first. Okay. So did you at least follow this completely? Of course, there will be seeds of doubt always. That is okay. When you start thinking about it, you will understand it. But at least did you get the big picture of what is happening in the system?
Yes.
Okay.
Yes.
So now I will ask you a question. Then, since you have already understood, let's bring. Okay. So now we'll bring our favorite component. Right? So what is our favorite component? Our favorite component is the cache. I will not write the result space. I'll just write that there are. Now you assume that okay, let's write result space for now, and then we can check, remove it out. Let's say the result space is huge enough to store all the table entries. I mean, just an assumption that the result space is able to store all the entries, all the translation entries. It's just an assumption, but it's okay to have. Okay. Now the process zero is mapped 4 entries. So the process zero will be somewhere here with 4 entries. Okay. First of all, before this, why did you add cache? So why did we come up with a hardware structure called cache?
Because main memory is slow.
Because main memory is slow, right? So because maybe it's taking 100 cycles, maybe this cache is taking 1 cycle, so I want to have a hit. Now, why did I come up with this page table and all those things? Because I wanted to support virtual memory. Now let's see the journey of an address, right? So this guy generates an address for process zero. Let's say it generates an address 0x83. Now, where do you have to go and access? Now, can you access the cache directly?
No, now you need to
No.
go to the main memory.
Now I go to the main memory, get the translation, right? I bring the, okay, I get the translation and maybe jump to somewhere here, right? And then give that data to the cache and to the CPU. Okay. I'll repeat again. So when this process generates an address, this is a virtual address. Now I am convinced that this is a virtual address. I go to the result space. Let's assume that it's always linked in the result space. I will translate it. Maybe it's saying it's the address. Maybe it's saying, so can it say 0x23? Can it say 0x23? Do you think it can say 0x23?
No, sir.
No, yes, it's right. Why? Because it's still the result space. So this will never happen. So maybe it generates an address 0x40, which means that I go here. And then I read that particular data and give it to the CPU and the cache. Now, was there a row? And next, let's say CPU generated one more address. Can you search in the cache? No. You will again have to go to the main memory, read it maybe somewhere here, put it in the cache. But why are you then having the cache in the first place? It doesn't make sense to me at all. See, any address that you are generating, you are anyway going to the main memory. So you can anyway get the data. So why have cache at all in the first place? So any answers to this?
Sir, can we, after decoding the physical address, can we go to cache?
Yeah, but why do you want to go to cache? Right? You already have the data. Okay. What you were saying? Okay, it's a good point. Excellent.
Yes, sir.
Yeah. So what somebody is saying is like, oh, sorry, I don't know your name. But what you are saying is excellent. What you are saying is, okay, you decode the address, then you come here, you got the address 0x43. So now I go to don't go to the main memory. I search in the cache. I go back and run and search whether 0x43 is there. If it is in the cache, then I go to the main CPU. But if it is not there, then again I come back to the main memory and search and then give it back. That's what you are saying, right? You will do.
Yes, sir.
But every access is now going to the main memory. That's the thing, right? Whether it's your solution or my solution, every access I'm going to the main memory. Agree? There's at least one access to the main memory. But I had the cache. Why did I build a cache? Because I didn't want to go to the main memory. Because this main memory is off chip. If you remember, it is off chip. Because this is the chip, right? So if every access, if I'm going to the main memory, why have the cache at all, right? So maybe reading here is simpler than actually running back to the cache, searching in the cache, because even if it's a hit, I would have already paid the penalty for coming to the main memory. So anyway, I would read the data and send it back rather than searching in the cache.
So maybe similar to how whenever we have a miss in the cache, we also keep those particular table entries in the cache.
Okay.
So at least for some of them, like we can decode it in the cache itself.
Okay. Your answer is right, but did everybody follow why this is an issue? That going for every access going to the main memory is an issue?
Yes, sir.
Okay. So now what Devesh is saying is an intelligent mechanism. What she is saying is, what is this page table? This page table is again some data, right? So you're converting the 0x83 to 0x43, right? So maybe I will keep some frequently accessed translations in this cache. Frequently accessed entries in this cache. Is this okay? Then what am I doing? I'm going and searching in the cache for that translation. If it's a hit, then I already got the physical address. Then I search in the cache. I never have to go to the main memory at all. Does the solution work, or is there a problem with the solution, or are you happy with the solution?
Sir, so will it have the translations for the blocks that it is having or any other?
No, can you guarantee that? Yes, it's a good question. This is what I ask for interviews generally. So people say that people actually generally give sometimes wrong answers. So do you think that you can guarantee that? Is there any relation between, okay, the other way to ask this is, is there any relation for the blocks in the cache and the translations available in the table?
Yes, sir.
Yes, sir.
Why do you say yes?
Since we translated, we are going to access the block.
No, right? It need not be in the cache.
It need not be in the cache, but we are accessing it. So we keep it in the cache.
No. So what Amit is asking is this. Let's say I generated 0x83. I got this translation in the cache. I got this translation somewhere here. I got this translation here. Okay. So I got 0x43. Now what is the 0x43? This 0x43 is an address that the CPU is trying to read some data or write some data. Now, are you guaranteed that 0x43 is available in the cache? The data location is available in the cache?
Sir, but that's not guaranteed, sir. But when you're bringing a block, you bring the translation and the block into the cache, right?
Yes, but the block might have been kicked out from the cache.
Okay, so then you should probably kick out the entry as well if we're not doing that then.
No, you're forgetting one more thing. This translation is not for a single block. This is for a page, which is pretty huge.
For a page, yeah.
So if you kick out a block, there is no kicking out a table entry, right? Because the table entry is mapping huge number of blocks. Now you can say, if I kick out all the blocks of the page, I will remove the page table entry. But how are you making sure that then you will have to have one more hardware structure which is keeping tab of have I kicked out all the entries of this particular page or not? Agree? Okay,
So could you please explain this part again?
Okay, but the thing is, this design itself is wrong. Okay, I'll take 4 minutes and then we'll close the class. Okay. Again, I repeat, because I'm on video, the design that I'm explaining you is actually wrong. Such a design doesn't exist. It's just for your understanding that I'm thinking about this design. Okay. So now let's say we have went with Devashish's design, right? Okay, so let's put the blame on her. Let's say it's Devashish's design, so that even if people know that it is fault, it's the student's fault and not the faculty's fault. Okay. So now she is keeping the entry here. Okay. So what is the entry? It is 0x83, 0x43. The page size is 64 bytes. Okay. I can have the cache block size. Let's say the cache block size is 64 bytes. I can have it, but generally it doesn't make sense, right? Because cache is pretty small when compared to the main memory. Maybe the cache, so the page size, we already saw that it's 64 bytes. Okay. The block size, cache block size is maybe 4 bytes. Okay. So one page is made up of how many blocks? How many cache blocks?
8 blocks.
Yeah, 16, man.
Sorry.
16, right? 16, right? Yeah, 16. 16 blocks. One page is made of 16 blocks. Okay. Now, the question is, you generated a page address. You generated an address. You figured out that this is the page address 0x83. You translated it to, so this was the virtual page address. You translated it to physical page address 0x43. Okay. The first question that you have to ask is this 0x43, this is a page address. Then you will attach it with maybe some block address. Is this part of the cache?
No, sir. That can
No.
change when the main memory changes, is swapped in or swapped out.
No. Okay, I think I am not able to. Okay. When the CPU generates an address, like it's a 32-bit address, let's say it's some big address. Okay. It has, forget about the cache, it has an offset and page address. In this particular example, what is the number of bits in the offset?
Two?
No.
So 2 only, right?
Why 2?
Cache block size is 4.
No, right? I am talking about the page address. So then now when the CPU generates an address, you are trying to access a page. Let's assume that there's no cache.
Then 6
bits, right? Why? Because the page size is 64 bytes.
64.
Right? So you are not using the 6 bits. You are using the remaining as the page address. So this is the page address. Okay. Then I come to the physical address 0x43. And then you tag along the remaining in the 6 bits, right? In the 6 bits, right? The 4. Okay. So now, anyway, I will be explaining it in the next class. Even if you don't understand it, it's okay, because it's very difficult to explain this entire thing in just 5-10 minutes. So when the CPU generates an address, it's a virtual address. For what is it generating? Let's ask for what. Is it generating for a byte, for a page, for a block, or what is it generating for?
For a byte.
Yes, that you should never forget in your life, right? It's always for a byte, at least till I am alive. Maybe for your generation it might change. It is generating for a byte. Let's say it's a 32-bit address. Now the first role that you are, or the first task is what? You have to access the page table entry. Okay. Agree? You have to access a page table entry. Okay. So now if you want to access the page table entry, right, I have to divide it into page address and offset. The same address, it's the same address, I'm not changing anything. If the page size is 64 bytes, right, I allocate 6 bits here and the remaining as page address. Agree? So maybe if it's 32 bits, then 26 bits here and 6 bits here. Agreed?
Yes.
Okay. So now I got the translation done. Now I want to search in the cache. If I have to search in the cache, I take the same address, and it's the same bits. I take the same bits. Now again I split it into offset. When I say split, I am not splitting it actually. Like I'm not taking a scissor and splitting it. It's just a virtual split. If the block size, cache block size is 4 bytes, how many bits are there in the offset?
2.
2 bits. If it's a fully associative cache, how many bits are there in the index?
0.
0. So the remaining is the tag. Okay.
Sir, why are you taking the same bits? We should
No, it's
take the
just a-
translated bits, right?
Yeah, sorry. Yes. Excellent. Yeah. So yes, you're right. So the physical address is to virtual address. Sorry. Yeah, excellent. Okay, I think you guys have understood it better than me. Yeah, so this was a virtual address. What he is saying is I generated a virtual address. It got translated to physical address. So the physical address is what I'm splitting it up. So when I am accessing 0x43, I am splitting it up into bytes. Now, let's say 0x43 looks something like this. So this 0x43 is storing here, and then it has, let's say it has, in this, I am taking some 2 bits for the block. If it's 0x43, then it's maybe 1, right? Is it guaranteed that this block will be part of the cache is the question. Is the address 0x43, can it be part? So this is just giving me a physical page address. So I can't even have this. I attach this later with 2 bits. So I make the entire address. So is that block byte available in the cache? The answer is need not be. Okay, the last part, if you didn't understand, it's okay. We'll come back to it later. But I hope you understood why we want to keep some entries in the cache. Is that clear?
Yes.
Okay. So we'll come back to this. Don't worry about the physical address and mapping. Maybe I should not have started before the end of the class. But I hope you are clear that I cannot always go to the main memory, get the translation and fetch it to the cache. So I keep some entries in the cache. Now, if I keep some entries in the cache, then I actually see the translation done here and then search in the cache. Is this okay? And if it's a miss, if the translation is not available, I go to the result space, get the translation and maybe search in the cache or in the main memory, we'll see it later. But if it is a hit in the translation cache, then I search in the cache and give it back to the CPU. Is this okay? Forget about the address translation. We'll come back to it in detail later. Is this okay?
Yes.
So like these translations have to change whenever there's a swap in and swap out in the main memory, right?
Why?
Oh,
okay,
so,
yes,
yeah,
yes,
so
yes. You have to update the
okay,
entries.
yeah.
Which means that this block can become dirty.
Yes, sir.
But generally, this is not kept in the cache. You might have heard of this term a lot more number of times than you could have thought about it. It is stored in a separate hardware structure. Can anybody guess what the structure is called? Yesterday also I showed, when I showed something, I showed you that I had written something there. What is that hardware structure called? You might have heard this term. I'm sure that you would have heard this term. It's called TLB. It's a buffer called translation look aside buffer, which sits here, which has all the recently buffered translations available. So it's actually hardware. So that sits next to the cache. But there are some design issues with that also. We'll see in the next slide. Yeah, as I said, please don't worry. Whoever is listening to the video also, don't worry about this entire junk. I should not have introduced before closing the class. But I hope you understood up till here, like what is the design? Why did we come up till here? Like, why did we have a reserved space in the first place? Once we have the reserved space, why should I keep some entries in the cache? Because I have to go to the main memory and then get the translation. So I don't want to do that. So I keep it in the cache such that if the translation is available in the cache, then I get the physical address and search in the cache directly. If you understood that, I think that's more than enough. That's the goal of this today's class at least.